Okay, I just wanted to have a kind of a quick run through of some of the principles of electromagnetic radiation. These are things that we worked on in Remote Sensing 1, and just a quick review of a few of the things and maybe adding a little bit of depth to some of the things that we learned about it the first time through in Remote Sensing, about the interactions between the energy that comes from the sun to us and how it interacts with the atmosphere and ultimately in the surface of the earth. So when we look at the principles of electromagnetic radiation, or how electromagnetic radiation reaches us here on Earth, there really are a couple of types of error that we have to consider in remote sensing at first. And these we categorize as generally as radiometric error and geometric error. Radiometric error, of course, are effects that happen to the radiation as it passes through the atmosphere, both on its way in and on its way out after being reflected or emitted by the Earth's surface. And so, we do some corrections. We do some in this course, and then there's also some radiometric corrections that are applied before we receive the data. Geometric correction, of course, is the type of correction that's applied to improve or to make more useful the georeferencing or the geographic location of the reflectance data that we then format as images. Normally put them into some form of a map, a projection, or something that we can use and combine with other forms of georeference data. So again, we normally refer to this as pre-processing, although it is processing, but it's usually the first sort of processing that we do to these data, both at the agency level, at the levels of the different agencies that collect the data, and then here once it comes into our hands, we sometimes apply corrections and pre-processing to them as well. The best example of this that you guys are familiar with is the radiometric correction that we do, the seasonal radiometric correction that we do when we're doing change analyses, and we have remotely sensed images from different dates that can be corrected somewhat for the effects of the difference in seasonal solar elevation, high sun in the summer, low sun in the winter. And so these are some of the steps and a more or less logical order of the kinds of pre-processing that are applied to imagery as it's being corrected, both for radiometric and geometric inaccuracies or differences that we need to correct for to make it more useful for our purposes. So, this just gives you a sense of what you're looking at. Every time you're looking at an image, by and large, you're seeing something that is a corrected image, and it's been corrected in all these different ways, particularly in this order. And so the sun again is a medium-sized star. It is very active if you look at it closely, and we have some nice satellites that are solar observatories that we have a much better understanding of what's happening on the sun, certainly a much better visualization of what's happening on the surface of the sun, how dynamic and how active it is. And so the energy, the electromagnetic energy that we understand is coming from the sun, we use the wave model to understand this, and this does yield a continuous spectrum, continuous from the ultraviolet up through the visible and through the infrared and out into the thermal infrared as well, so out into the very long wave thermal infrared. And there quite honestly is probably, even longer wave radiation that we don't really consider much in remote sensing, certainly as coming from the sun, although this is something that's used, quite a lot in, in astronomy and in other forms of remote sensing. Again, astronomy is another category of remote sensing that we're not really dealing with here, because we're doing principally Earth and planetary remote sensing. And so, as this energy is transmitted to the Earth through the atmosphere, some of it's received. What happens once it gets through the atmosphere, the processes that take place in the atmosphere of scattering, absorption, but then you also have the emission of long wave radiation, of heat radiation, absorption and re-emission of this, and then you have reflection of shortwave radiation, shortwave being visible, a bit of ultraviolet visible, and near infrared. And so, this again, just sort of reestablishing our understanding of this process. So we sometimes use these what are termed blackbody radiation curves, and these are theoretical curves of the energy that would be or is emitted, I guess you would say, by a body at a particular temperature in a vacuum. And so these curves are have very similar shape to them. As you can see, they tend to shift to longer and longer wavelengths as the temperature of the object drops, right? So colder objects, this curve that is a similar has a similar shape to it and is a similar function, are descriptive of the level of energy, the radiated energy of a particular body specific to wavelength. And so this curve is a way of does a number of things for us. It allows us to understand where the peak level of energy for a given energy source is in terms of wavelength. So the sun, as you can see, its peak is right in the visible. Here's a tungsten filament like you would see in an incandescent light bulb, and again, its peak is somewhere in the near infrared, right? And here's an object or a body at the temperature of the Earth, and again at 300 Kelvin, which is a nice balmy kind of temperature for us, and it peaks right around 10 micrometers in the thermal infrared. This is why we call this the thermal infrared, because we're able to sense the radiative temperatures from the Earth's surface. Again, here are a couple of other curves. Now these curves are they are similar, and there is a function that describes that similarity through it's Wien's law, or Wien's law, that allows us to calculate the temperature of an object based on the wavelength of its emitted energy. Okay, as this energy passes through the atmosphere, there are some different things that happen to it. Some of it is reflected back out into space and doesn't reach the Earth's surface. Some of it is absorbed, and then some of it does pass through the Earth's surface. And this diagram gives us a sense of the cumulative effects of some of the different components, relatively small percentage components, of the Earth's atmosphere. Nitrogen, of course, free nitrogen being the dominant gas in our atmosphere, and oxygen, of course, oxygen and ozone, also a relatively large component of the atmosphere. And then some of these other gases are natural and human-produced greenhouse gases, and of course H2O, a very naturally occurring gas in the atmosphere. And so if you look at this, you can see the cumulative effect, and then this gives you a sense for what energy will actually reach the surface of the Earth. And you can see these windows in the atmosphere that open up at specific wavelength ranges across the visible, which is very open, with some minor absorption there in through the green and into the red and so on. And then you have these spikes of absorption and reflection or scattering that are occurring at longer and longer wavelengths. So you can see, particularly when you get into the near and mid-infrared, there's less and less of the spectrum available to us as remote sensors to be able to see things. So if you tried to look in this part of the spectrum, you're not going to be able to record any data. You won't get you get very low, very low numbers, which are probably largely a result of noise or some other effect that's not coming from from the target that you're trying to sense. Again, so this is a really nice and useful diagram for us when we're thinking about what we can see and what we can't see with the instruments that we're working with. So as I mentioned, Wien's displacement law, this is something that we are using and will use and have used, I guess by now, in this first activity, where we're going to use a constant, Wien's constant, which is given here, to calculate the in some instances the wavelengths, and in some instances the temperatures. Relatively simple formulation here that involves a very minor bit of algebra or algebraic work by you to calculate either wavelengths or temperatures, given knowing the other value, either a temperature or a wavelength. So again, this gives you a little different look at the curves, blackbody curves for the Sun and for the Earth. Again, slightly modified here, but again, this is we want to get through the first part of this to get a sense for what we are trying to sense, not just with Landsat, but with some other sensors that we have and will be working with in this course.